The next SPC tool that we're going to be covering is control charts. Before we can begin discussing control charts, we need to have a little bit of a discussion and a background on the nature of variation. So first off, there's two types of causes for variation within a manufacturing environment. Those include common causes as well as assignable causes. Common causes include inherent variations that are naturally part of a given process. And because they are natural variation, this variation is going to be random in nature. Voltage fluctuations is an example given in this slide. Environmental changes, which are there's totally random with some trends, but in general, it's something you can't really predict too far out. We would expect in a natural environment, all things being equal, flipping a coin a bunch of times, you'd get about 50% of your flips would be heads and 50% of your flips would be tails. It would be weird, it would be strange, it would be abnormal to have a coin that always flipped heads or predominantly heads versus tails. The other types of causes are assignable causes. These are non-random variation that can occur, things that don't occur by chance. In other words, if an assignable cause is detected, the process should be looked at more closely and the source identified because a non-random event is acting on your process. If a penny is going to show me heads over and over and over again, I'm going to try to investigate. It's really unlikely that it's heads all the time. That coin is either weighted or somebody is flipping the coin in a very specific way such that it always gives me heads no matter what. So some examples of things that in a manufacturing environment could be an assignable cause include things like the quality of the raw material that you're using. One vendor gives you really, really good quality material. The other one gives you really bad quality or questionable quality material. And you see in the output of your process, then all of a sudden there's a shift. One material you're running at really close to target, and the next material you're all over the place. So that might be a source of an assignable cause. Another one could be changes in machine settings. You were running really close to your lower spec limit, and then all of a sudden somebody hits a knob and now it's set to something higher, or maybe somebody thought they were running a different process with the wrong specs and you have a actual shift in your process. That's something that shouldn't occur randomly. That indicates something is acted upon it, not randomly, that can be investigated and hopefully fixed before you've produced any waste. So with the idea of assignable causes and common causes in mind, let's talk about what a control chart is. A control chart is a chart that's used for monitoring and controlling ongoing processes. It consists of data points plotted in sequence over time and with an upper control limit, or what we're going to refer to as a control limit, and or a lower control limit on that chart, as well as a center line. It's used to find out whether or not your process is in control. Helps you determine when an assignable cause has come into play and the process needs to be analyzed or investigated. The control chart, you're going to find out as you go through this, as you're using the control chart, we would expect nice, healthy, random variation in the outputs of your process. If you are getting anything other than that, if patterns start to show up or something unusual relative to the other data that you've plotted appears, that is cause for investigation, and control charts can be used to go and pinpoint that, again, hopefully before you've actually started to produce bad product and scrap. Control charts are also known as Shewhart charts, in honor of Walter Shewhart, who developed the charts in the 1920s. Since control charts are designed to help us control our process, the question is, What defines an out-of-control process? Some of these things could be or include a single point going beyond either the lower or upper control limits. Also, you can have a run of 7 consecutive points continuously increasing, decreasing, or not changing at all. Other patterns include things like trends, mixtures, and stratifications. In the next slides, we're going to actually demonstrate what each one of these different conditions could mean. So this slide is going to show you what the different out-of-control process indicators could be. First, a little bit of a explanation of the control chart that you're seeing. You're seeing a annotated control chart. You have 3 zones above the center line and 3 zones below your process center line. The first zone, or each zone, is defined by a standard deviation, an additional standard deviation from your process center line. So zone C, where we expect the vast majority of our data to fall, is plus or minus 1 standard deviation from the process center line. Zone B is between 1 and 2 standard deviations from the process center line above or below the process center line. And zone A is between 2 and 3 standard deviations from the process center line, either above or below the center line. The control limits are defined as the border between is the border of 3 standard deviations above or below your process center line. So going from left to right, the different out-of-control process indicators that you might see according to the Western Electric rules are the 1 point beyond zone A, meaning even a single subgroup of data that falls outside of zone A, that is a cause for investigation, and assignable cause is possibly in play. The next out-of-control indicator in this set is the 2 out of 3 points in zone A or beyond. So while we would expect that data points would fall within plus or minus 3 standard deviations of the center line, we would not expect it to happen 2 out of 3 times. That's very statistically unlikely. Next example is the 4 out of 5 points in zone B or beyond, which again, it's more likely that data would fall in zone B. We would still not expect that 4 out of 5 points would be in zone B or beyond on any given process. That could indicate that the process has shifted. On this next slide, we're going to show you the chart again. We're going to start over again and see some other potential indicators. The first one, going from left to right, is a mixture. And in this case, using the Western Electric rules, a mixture is defined as 8 points on both sides of the center line, but none of them falling within zone C. Again, zone C is very close to your center line. We're going to talk later in future slides about normality. We would expect most data to fall in zone C, and in this case, it's falling around zone C, but nothing is falling directly in zone C, which could be indicating something, and we'll talk about that when we talk about histograms. But that is something that's worthy of investigation because you might need to separate out multiple control charts. The last indicator that's demonstrated on this chart is the stratification, 15 consecutive points in zone C. Now, while it would be absolutely expected that most of our data, above 60% of the data, would fall in zone C, we would not expect that 15 consecutive points would fall in zone C. That could indicate any number of things that you need to investigate, from cherry picking your data points to your machine that you're processing with is improperly lubricated, so it's about to get stuck and become jammed. In other words, no matter what you need to be aware of is when you see these process indicators, it could be that nothing is going on. However, it is very likely that the process is shifting. Therefore, you should go and investigate further. So in the previous slides leading up to this one, I talked a lot about the words control limits and your process is in control versus out of control. So what exactly are these control limits? So in this slide, we're going to talk both about control limits as well as specification limits. So First off, let's talk about control limits. And remember, control charts are designed to track whether or not our process is in control. Control limits are calculated based on the actual process data that you've already acquired for plus or minus 3 standard deviations from your center line. This ends up, if you've ever heard the term 6 sigma, this is what it's referring to. It's a spread of 6 total standard deviations that we expect your data to fall within. When a point or a subgroup of data falls outside of these control limits, that indicates that the process itself is out of control. It's not a stable process. There's a assignable cause likely that is in play, and you need to go investigate. Now, specification limits are a completely different thing. Spec limits come directly from your customer. They are parameters for tolerances. Other words for spec limits or specification limits include engineering limits and the before mentioned tolerances. When a point falls outside of specification limits, that indicates that the part you've just manufactured or the part that you've just measured is out of tolerance, meaning you can't ship it. It is bad. It is somehow you need to take some action. It does not necessarily indicate that your process is either unstable or out of control. So these are completely different things. Spec limits come from your customers, be it internal or external. Control limits come from your data and what your data has historically done. So now that we've discussed what the difference is between control limits and spec limits, the next thing that we're going to talk about are the types of data that you can record on a control chart. There are 2 statistical types of data. The first statistically recordable data that you might want to record, and is by far the most common type, is variable data, which is the same thing as quantitative data. It's anything that you can measure with a number, things like length, width, height, viscosity, volume, depth, anything that you can take some sort of measurement instrument or have a measurable value number that you can go and put on a piece of data, that would be variable data. Now, if you have data that you can acquire that is statistical in nature but can't necessarily be recorded in the form of a measurement, things like true or false, pass or fail, things that are qualitative in nature, that would go into attribute data and would be recorded with attribute type charts. Because variables and attributes are different in how they are recorded, they therefore have different types of valid control charts that you can use with them. Variables at their core are measurements of some kind. They're quantitative, and they have specifications, spec limits, tolerances, a line of delineation that separates between good product and bad product. So valid charts, control charts that you might see for variables include things like the Xbar and R chart, the Xbar and S chart, and the X and MR chart. We will cover what each one of those charts are as we go through the slides. But just a quick overview of the most common one, the Xbar and R, that is the average value of your samples within a subgroup plotted onto the control chart, and the R is the range, that's the largest minus the smallest value within that subgroup plotted onto a control chart. Attribute charts are a completely different nature. There is no spec limits. Charts include things like the P chart, NP chart, C chart, and U chart. The most common one for defective units is a percent chart or a P chart that shows you the percentage good, and you can actually flip that and call it a Q chart. Then you can look at the percentage bad instead of the percentage good. So now that we've talked a little bit about the types of control charts you might see, we're going to now talk about how often you want to collect data and put it onto a control chart. There are three general categories of inspection sampling rates that you can do in any given process. Your first option is to inspect everything, 100% inspection. Your another option that you have is not to inspect anything at all. And then there's sampling, where you inspect some representative sample of your data. So there's advantages and disadvantages to all of the different options, and we'll cover that right now. The advantage to 100% inspection is that you literally inspect every part that you produce, and you have a handle on everything that's left the factory. If you have a good database system where you can go and track all that, it's not a big deal to go and then retrieve that information if you ever have a customer complaint, and you can prove that this was either a good or not good part. You can correct any issues that occur as they happen. The problem with 100% inspection is that it is very expensive. It requires time to measure everything. It requires effort to fix anything. It is a very expensive process. Now, in certain regulatory type situations, you may not have a choice. This is your only option. But if you're destructive text testing, this isn't even an option at all. You can't do it, because if you have to do tensile testing and you do 100% inspection, you've literally broken everything that you are trying to sell or produce. So 100% inspection gives you visibility on everything you produce, but it is extremely expensive. The other extreme is no inspection at all. The advantage to that is it's cheap, at least up front. It doesn't cost anything to not look at any of your product that you produce, then you just go ahead and ship, whatever you produce. The downside to that is you have absolutely no idea what you're shipping. You don't have a clue if the product that you've produced and shipped is anywhere meeting the requirements of the customer. At the very least, you're going to have complaints. At the very worst, you're going to cause failures, and you're going to have, you're going to go out of business because you're going to have a reputation as not being able to produce quality products eventually. Anytime any shift in your process happens, you're going to be unaware of it, and you're going to make bad product. Now, sampling is a happy medium between both of these. On the one hand, it's nowhere near as expensive as 100% inspection up front, and it's nowhere near as expensive as no inspection at all down the road. You inspect a sample of a representative sample, a rational subgrouping, a rate of your quantity produced, and it actually in some ways gives you better visibility than trying to record everything at all. It weeds out a lot of the natural variation, and it allows you to focus on just the parts that are shifting, assuming that you track this information properly. Very important to realize there's different ways you could handle it, but sampling for SPC purposes is the way to go and the way to gain the most value. Now, there's the question about, well, if I'm sampling, how can I know if everything that I produce that I have not actually sampled, if I'm not doing 100% inspection, is still under control or in tolerance? And we're using statistics, and we're using the nature of the fact that we're going to talk later about the bell curve and whether or not we're actually able to produce things repeatably. But for right now, sampling is going to allow us to, with statistical certainty, depending on how often you take your readings, it is going to show us if it is likely or not that something is changing. Because it's sampling, it's a model. The statistician whose name is Box once said that all models are wrong, but some are still useful. We're going to be using SPC to generate a model of our process. And by doing that, even if it's not an exact model of everything that's being produced, we may still be able to see over time that things may or may not be changing in our process. In this slide, you're tasked with counting the number of the letter F's, the occurrences of the letter F, in the following two paragraphs. So I'll let you go ahead and go through this. Go ahead and you can pause the video right now if you want, and go ahead and try to count through these. if you've just resumed from a pause, if you find that you have counted a total of 12 Fs between the two paragraphs, you would be correct. Anything less than that, you've missed a couple of Fs. So the question is, why is it that the first time you go over these paragraphs, you tend to miss a lot of the letters that are present? In this case, the word finished, that's 1. Files, that's 2. Are the result of, that's 3. That tends to get missed. Years of, that's 4. Scientific study, that's 5. Combined with the experience of, again, that's another letter of that tends to get missed. That's number 6 for the first paragraph. In the second paragraph, 4 centuries, important projects have been deferred, that's number 2. By weeks of, that's number 3. Indecision, and months of, that's 4. Study, and years of, that's 5. Formal, that's 6. Debate. Humans are really, really bad at repetitive operations, at doing things that are granular. We tend to fill in the blanks. When we read a letter, we look at the first letter, maybe the last letter, and we fill in everything in the middle based on its size. We usually figure out what word it is. We very rarely read phonetically. Computers, on the other hand, completely different story. They're not so good at finding the meaning of a sentence, but they tend to be very good at being able to tell you all the statistics that have to do with the sentence and be able to break down any calculation based on it. An SPC package like WinSPC is there to free you, the human, to allow you to give you time to do the things that humans are good at. Things like using your experience and your imagination and your thought processes to come up with a reason as to why an assignable cause is in play, to investigate and to figure things out. You're really bad at actually doing the actual inspection and running the calculations yourself. People are not as good or proficient at math, certainly not without making, or the potential for making, mistakes. Machines, on the other hand, are really, really good at eliminating repetitive type mistakes, but they have no ability to go and investigate and try to figure out why things have occurred the way they have. So I hope this example can really illustrate to you why you might want to implement a system that minimizes human interaction as much as possible for the data collection and for the calculation of control charts, but does maximize the use of humans for actually figuring out what goes wrong in any given process. So within variable control charts is the very important concept of the subgroup size. There isn't really an industry standard term for what I'm about to describe. There are words that in various textbooks will be used interchangeably. At least within the confines of this class and within the confines of WinSPC, the subgroup is always the point that is plotted onto a control chart that is compared to other points that have already been plotted onto the control chart. So subgroup size is how big that subgroup that gets plotted on the control chart is, how many individual readings or individual what we refer to as samples are averaged together, turned into a subgroup, and plotted onto the control chart are. So the way we call it, the way it is on this slide, the number of parts measured at the predetermined frequency. That's a quick way of remembering what a subgroup is. So for example, if you record 5 readings for temperature every batch, your subgroup size is 5, and that might get plotted on a control chart. 3 readings for height every hour. That's another possible example of how you might have a subgroup set up. Now, if you recall from the previous slide, we started talking about the different valid control charts that you could have for either variables or attributes. We will cover a little bit more in depth about the different possible valid variable control charts, or at least the very common ones here. The Xbar and R chart is probably the most common chart. It is anytime you have a subgroup size that is larger than 1. You tend to use it when the subgroup size is also smaller than or equal to 7. However, your mileage may vary based on what you're trying to do with your process, but subgroup size, you're plotting your X bar, that's your average of your subgroup, and the R, which is your range, your largest minus your smallest value within your subgroup. You plot it on a combo chart, a top chart and a bottom chart. As you're going to find, hopefully when you go through some of these examples, you're going to find out while most people tend to focus on the X-bar chart, which is your average value for what gets plotted, the volatility of your process really is captured more in your R charts, your secondary chart that really illustrates just how capable you are of producing product consistently. We'll talk about that more as we go through other examples, as well as we talk about things like the actual capability analysis part of the course. But for now, we're going to continue on. Xbar and S is very similar to Xbar and R. So the top chart you're going to be plotting is your average of your subgroup. S in this case is going to refer to variance or standard deviation, where it's going to actually plot a value that's going to be what's your standard deviation for the data points that you've just plotted, for the subgroup that you've just plotted. That tends to work better when your subgroup size is greater than 7. And again, your mileage may vary if you are from a different school of thought or your process is a little bit different. Maybe you may not want to switch to an Xbar and S chart until your subgroup size of 10 or 9 or whatever works for you. But within WinSPC, at least, there is no magic number that we're going to flip between going from a subgroup size, between using by default an Xbar-R chart versus an Xbar and S chart. It's really up to your personal preference what you want to see and what your quality engineers are used to seeing as far as what is the best chart to use in your process. An X and MR chart is the X and moving range chart. This is only used when your subgroup size equals 1. When your subgroup size equals 1, you plot every single individual reading onto the control chart as a subgroup. But because you can't do any comparative analysis on a single point of data, you can't do an average on a single point of data, you can't do any sort of capability analysis on a single point of data, there's no difference between a single point of data. Therefore, you need to have some sort of comparative statistic that you're going to use to show volatility for your secondary chart. And the way that we do that is by using something called a sub-range, where we define how many points back on a control chart, on an X and MR chart, do you want to look back to do your comparative analysis. We will actually do an exercise with X and MR, so it'll become clearer as far as how that works. But you absolutely can have a subgroup size of 1 for a control chart, both just in general with SPC, but as well as with WinSPC. We're going to go ahead and do an exercise now for the Xbar and R chart. So the scenario is as follows. The diameter of 5 pencils is measured every 30 minutes. The specifications of those pencils' diameter are to be between 6.7 millimeters plus or minus 0.5 millimeters. You are to plot an Xbar and R chart for the readings for the last 4 hours. This slide shows the data that you've collected for the 4 hours that you were doing your data collection. You see you have 8 different subgroups that you've collected over 4 hours, and you have, within each subgroup, you've taken 5 samples. Now that you have your data, your first step is to calculate your X-bar value for each one of your subgroups that you collected each half hour, and you are to also calculate the R value within each subgroup. Once you have this information, you have your X-bar for all 8 subgroups as well as your R for all 8 subgroups, you are to then calculate your X double bar value, which is the average of the averages, and your R bar value, which is your average of all of your R values. A quick refresher, anytime you see a bar that indicates an average And a bar on top of another bar indicates it's simply an average of averages. So if you ever see the notation with the bar on top, that's an average. The double bar is sort of a grand average. Your third step in the creation of an Xbar-R chart is to calculate your control limits. Now we have a function to determine our control limits. For the upper control limit, you can see it's your grand average, or your X double bar, plus A2, which is a constant that comes from a predefined source table relative to the size of your subgroup, multiplied by your R bar value. That will give you your upper control limit. Your lower control limit is your grand average, your X double bar, or your process average, minus A2 times your R bar value. Now that's just the control limits for your primary or upper chart, your X-bar chart control limits. Your R chart is going to have its own set of control limits. In this case, you have an upper control limit for your possible ranges. And in this case, it's going to be D4, which is a constant, again, from a lookup table, times your R bar value that you calculated in step 2. And that's going to give you your upper control limit. If you had a lower control limit, which in this case there actually isn't one that is applicable, you would multiply your D3 value times your R bar. In this case, it doesn't actually have a meaning, so we're not going to, or it's not a there's no valid lookup for that, so you're not going to get a value. It's undefined. Another thing to keep in mind is just a quick sanity check. Your range is a magnitude. It is a how big your largest from your smallest values are. You should never get negative values. You should never be able to get a value that is below 0. Step 4 is to actually go and plot your control limits for both your X-bar chart as well as your R chart. You're going to plot your upper control limit, your center line, and your lower control limit for your X-bar chart, and that's the stuff you calculated in step 3 in the previous slide. You're going to also plot your upper control limit independently for your R chart, so that you can go ahead and begin to start plotting the items you calculated in step 1 for each one of the charts. You're going to go ahead and plot all 8 X-bar values that you calculated in step 1 into your control limits for your X-bar, and then you're going to put your R values into your R chart, the ones that you calculated from step 1. Now that you have plotted your X-bar chart and your R chart, you can begin to analyze what you have drawn or what you've plotted. For the X-bar chart in this case, your first and second subgroups were falling within your control limits. However, your third and fourth subgroups are out of control. They look like they were actually falling below your lower control limit. Now, it doesn't necessarily mean that you've fallen out of specification, but the process itself has fallen out of control of what historically the data was expected to do. Afterwards, it looks like your process started going back in control again, but once you hit your last subgroup that you plotted, subgroup number 8, you were out of control, violating your upper control limit. In each one of those 3 cases where you fell outside of control, you should have tried to investigate had you been plotting this in real time. And you would have been able to plot this in real time had you some data, enough data historically to actually go in and begin plotting this. This is where WinSPC comes into play. You would have been able to catch these out of controls immediately and begin to investigate and determine if it was in fact a true positive or a false positive. We're also going to look at the R chart. You can see that all of these subgroups fell within your control limits. There are no specs for your range. Your literally, ultimately, ideally, you would want zero variation and you'd always want to hit your target. But since that is almost impossible to achieve, at least not in a cost-effective way, you want to get your range, you want to get the volatility of your process to where it is within historical consistency. There are no points that fell out of control. You would have or should have tried to investigate what was going on with subgroups 3, 4, and 8 to see why your process was out of control. Further, since this type of control chart was not done in real time, and you wanted to determine whether or not you were in control, the last subgroup that you collected is in fact the state of your process. So in this case, subgroup number 8 is currently out of control. Therefore, the process itself is out of control. You really should go and investigate what the cause for that out of control point is. These control limits came from your data. You calculated these control limits. It's actually based as the actual voice of your process. And since it is out of control, it's actually showing that there is something that is statistically significant that you're going to want to investigate. Now, were you to have plotted this data directly into WinSPC for real-time analysis, this is actually what your control chart would have looked like when you were plotting this data. You probably would have gotten an alarm, assuming that you had configured WinSPC to do so, on subgroups numbers 2 and 3, and you also would have gotten an alarm on subgroup number 8. You'll notice that there is a red out of control indicator on the upper right hand corner of the screen. That shows that the most recent subgroup that you have plotted is currently out of control, and that you should look for an assignable cause or a special cause as to why your process is out of control. We do have an exercise for you to go ahead and follow along with that you can do on your own that utilizes the example from the previous slides regarding Xbar and R chart creation. This exercise is available in the actual SPC Fundamentals training manual for you to follow along with. In this exercise, you are again producing radios. You are going to generate an Xbar and R chart for the data that was collected when you had sound output recordings or sound output checks for 4 radios that is measured every hour in decibels. The specifications should be between 70 and 90, 80 plus or minus 10 decibels. You have 10 hours worth of data based on your 4 radios per hour check. In this slide, you can actually see the data that you collected from 9 a.m. until 6 p.m. or through 6 p.m. for a total of 10 subgroups, each subgroup containing 4 individual samples for a total of 40 samples. Just as we did in the example, step 1 is to calculate your Xbar value for each subgroup, calculate your R value for each subgroup, and make sure to write them down. Step 2 is going to be to calculate your grand average or your X double bar value, calculate your R bar or average of your R values, write those down. Then you're going to want to go ahead and calculate your control limits, your upper and lower control limit for your Xbar chart, which is your primary chart. You're then going to go and calculate your control limits for your R chart, which is your secondary or lower chart. Because this exercise uses a different subgroup size, our values for A and D, in this case A2, D3, and D4, are different than they were when in our example we were using an subgroup size of 5. Make sure to use the appropriate constant values for your appropriate subgroup size. Go ahead and plot your control limits for both your X-bar chart and your R chart. Technically, it doesn't really matter if you draw your control limits before or after you plot your data, as they are intertwined, they are related. However, you sort of get a better feel for the meaning of the data if you tend to plot your control limits first and then plot your data afterwards, but you certainly don't have to. One of the advantages of using software like WinSPC to do this for you in real time is that it's going to draw all this stuff for you anyways. Something to note, just to take care with when you're doing this by hand, you probably want to use a ruler, you probably want to use a pencil, and very important, make sure your scaling makes sense, because if your scaling is off, it's going to be really hard for you to draw each one of your data points. So just take care to make sure that your drawings are actually going to be able to fit in the charts that you have available to you, and that the scaling is consistent. We did provide to you in the SPC Fundamentals training manual a set of charts that give you a pretty good scaling already there for you, but do take care not to squish the data too tightly. So this is the solution to the X-bar and R chart example. So here are the results for all of your X-bar values for each subgroup, as well as all of your R values for each subgroup. Ranges between values from 0 all the way to 15 for your R values, having to do with your volatility, and your averages are somewhere between 75 and 90 for the entire production run. Your X bar and your X double bar or grand average and your R bar values are all calculated. You should get 83.5 or something pretty close to that, depending on your calculator rounding issues. And your R bar value should be 6.5. Then you calculate your control limits. Don't forget your A2 value in this case is 0.729. There is no D3 value, therefore there is no defined lower control limit, and your D4 value for your R chart is going to be 2.282. You should get 88.24-ish depending on your rounding. For your upper control for X-bar, you're going to get 78.76 for your lower control limit for your X-bar chart. Your upper control limit for your R chart is going to be 14.83. And just eyeballing the data without even plotting it, you can probably already begin to see some trends, but the charts you're going to see on the next slide are really going to hopefully confirm some of those observations. So when you plot your control limits and your X-bar chart, and you plot your control limits for your R chart, and then you go ahead and actually plot the data points inside, you can begin to see what's actually happening inside of your process. Now that we've plotted it, you can go ahead and begin to analyze it. What can we tell from the charts? Well, there's a couple of things going on here. First off, you can see that subgroup number 2 fell below lower control limits. So did subgroup number 4. Everything stayed in control from then on until you got to your last subgroup, subgroup number 10. Your R chart is also interesting. So you had a number of out of control points for your X-bar chart, and you're going to have to, or you will likely want to investigate. The probability of you wanting to investigate is very high to pick an assignable cause. But your R chart is also showing some information. With regards to the volatility, you're not seeing a whole lot of volatility within the process. However, subgroup number 3, even though subgroup number 2 was in control with regards to the average, the range in between that data was 15. It was higher than your upper control limit for your range value. So you may want to see why your process was so volatile. Perhaps your process was changing dramatically. And just eyeballing the trend after that, it looks like things were getting worse from subgroup 1 to subgroup 3 with regards to volatility. But all of a sudden, maybe a change happened in the middle of that subgroup, in the middle of 11 a.m., and then all of a sudden things started getting better, and your volatility actually starts to go way down until the point where you actually have no range, there's no variation at all between subgroups on subgroup number 8 or subgroup number 10. So your volatility within your process seems to actually be getting better. However, your Xbar chart's showing you that while that may be the case, the averages of those values themselves are still a little bit straddling a little bit too, or beyond your upper control. Your process itself looks like it's changing and it's out of your historical control. Doesn't necessarily mean it's a bad thing, but it is something you absolutely want to investigate and have an assignable cause to it. Because while you are producing a product that has no variation within the individual subgroups, the fact is the last subgroup value that you plotted was also equaling your upper specification limit too. And that's something that you didn't even plot here. You don't really need to plot spec limits when you're doing SPC. That's not the function. The function is first to get you into statistical control, meaning to get you into a state where you are stable and your process is not shifting, which this process clearly is. But afterwards, then you can begin to look at what's going on. Why are you now straddling the upper spec limit? So if I were to just speculate, and you can't really know this without actually going to your process and actually doing real investigation, but if I were just speculating from what I'm seeing from the chart here, something happened around subgroup number 2 where you were straddling your lower spec limit. Your radios were just too quiet. Maybe somebody started trying to adjust that. Maybe they adjusted it too much to the point where it actually, somewhere in the middle of subgroup number 4, they had to maybe turn production up way high or way down, which actually caused things to be more stable, but you were always straddling that upper limit. You're playing very, very close to your upper tolerance, and thus, which is historically not what you had been doing, and it caused you to actually go out of control for your process as a whole. Now, up until now, we've been discussing the Xbar and R chart and how you construct them because they tend to be the most common and they provide, in most cases, the most value in helping you predict when your process is beginning to shift if there is a special cause in place. However, there's a number of reasons where you may want to actually do individual subgroup plotting, individual sample plotting, and you can do that using an X and MR chart and still be able to get some SPC value out of it, some predictive value with process control, statistical process control. Keep in mind, though, that it's probably not ideal to use these X and MR unless you have a specific need to do so. Generally speaking, you usually want to have a subgroup size greater than 1 to eliminate noise within your process. But we're going to go ahead and do an X and MR chart example right here. So in this case, you are again a pencil manufacturer and you have the diameter of a pencil is measured every single lot. The specs for your diameter of your pencils is 6.7 millimeters plus or minus a half a millimeter, so somewhere between 6.2 and 7.2. And then you need to plot an X and MR chart for the last 10 lots. This is the data for your X and MR pencil creation. You may notice you have a lot less data than you had for the radio example with the Xbar and R chart. And what that actually is going to do in practice, in practical functionality, is that you're going to lose some sensitivity to your process changing. You're actually less likely to catch when your process is shifting because you are not plotting an average of a subgroup, but you're going to capture a lot more noise and your control limits are going to reflect this. There's still value to it, and you're going to see it's a whole lot easier to actually do the calculations with an X and MR chart, which is why they tend to get used quite a bit. But generally speaking, you probably want to shy away from this because you can see you just have a whole lot less data relative to how much stuff that you've collected, how much stuff you've produced in your actual process. Now, just like you did with the Xbar and R chart example, you have 4 steps, but the 4 steps are just slightly different. You no longer have to calculate any Xbars because there are no Xbars. You just have individual points or samples that you're going to go and plot. you are going to have to go ahead and plot your MR values, your moving range, your difference between the current value that you have plotted and the most recent value previous to that you've plotted, assuming you have a subrange size of 2. We may talk a little bit about subrange size later on. The notation used in your MR values, those are absolute value symbols before and after your first and second values, meaning you only want magnitude, you only want positive values. So you only want you can either do this manually by taking the largest of the two values and subtract the smallest of the two values, or you can use, programmatically just recognize that if you do the smaller minus the larger and you get a negative value, you need to make sure that the value ultimately is going to be a positive result. Otherwise, the MR chart doesn't have a whole lot of value to you. Step 2 is again to calculate your averages, but in this case, you're going to be calculating an Xbar, meaning the average of all of your individual samples. And you're also going to want to plot your MR average, or MR bar, which is the average of all of your moving ranges. This is very important and a point that a lot of people get stuck on. The first subgroup of an X and MR chart has, by definition, no moving range. There is no point for you to be able to go and calculate a moving range. There is no previous value. Therefore, you need to make sure that when you do your average calculation, that it is by the amount of points you actually can calculate a moving range. In this case, your 9 moving ranges you can calculate, your average is going to be out of 9. Your average is not going to be out of 10. So take care. That first MR value is not 0. Your X bar, on the other hand, is absolutely out of all 10 points. You're going to want to make sure to include all 10 lot values for your X bar and divide by 10 in this case. Step 3, calculate the control limits just like you did for your X bar and R charts. The functions or the calculations are exactly the same, except you're using a different set of constants because your subgroup size and your subrange size is different. In this case, we're using what's referred to as a subrange size of 2. We're only looking 1 point back in history from the current value. So we're going to be using the E2 constant, which in this case happens to be 2.66. And for the MR chart, we are still using D3 and D4 because the MR, in this case, it's going to be the same. For mathematically speaking, you can use the same values. Once you have the values all calculated, again, I'd recommend probably drawing out the control limits first for both your X chart and your MR chart, and then plotting the data points afterwards. But again, you don't have to. Once you do this, you can then begin to analyze the data that you've plotted. From what we can tell from the X chart and the MR chart, there are no points that are falling out of control. Therefore, the process itself is in control. Now, that's not to say that there might not be something you want to investigate. If you had your own set of control rules that you wanted to follow or something that you wanted to recognize, having this plotted out in a control chart, you can still begin to see patterns, but in the strictest sense from how you calculate control limits, all points are within control and are randomly varying about the center line, as we demonstrated earlier on when we showed different types of control scenarios and control violations. And your MR chart, also all points are in control and seem to be randomly varying around the center line, which is exactly what you want. And this is a great example of why you want to actually use SPC rather than intuition. If you had begun tampering around and started trying to change your process for your pencil diameter around subgroup number 8, you might have shifted it adversely where you would push it too far, your process too far down, and you may have gotten some out of control points because naturally when this process was moving forward between subgroups number 3, or rather number 4 and subgroup number 8, that was just some natural variation where it happened to be going up in 5 consecutive points and it came down naturally again. So this is an example of where you really want to exercise discipline in not tampering with your process and allowing for natural variation, not trying to control control your process when it doesn't need to be, when there's no assignable cause in play. You would have made things worse likely if you had tried to adjust somewhere around subgroup number 8. You would probably have caused your values to actually fall below your lower control limit, and maybe even below your spec if you were not being careful. So letting your process do what it needs to do, that is the major advantage of SPC. Not just showing you when things might start be going wrong, but also to show you when things are actually behaving as they should be, or at least as they are expected to. And if you had plotted this data in WinSPC in real time, this is what it would have looked like, or what it may have looked like depending on your other settings. Here's an exercise for an X and MR chart that you can do on your own, and like all the other examples, this one is inside the SPC Fundamentals training guide that you can follow along with. In this exercise, you are again a radio manufacturer. This time, one radio is measured every hour. The specs for the radio are between 70 and 80 and 90 decibels, 80 plus or minus 10. Plot your X and MR chart for the last 10 hours. Now you can see in this slide you have your 10 subgroups taken between 8 a.m. and 5 p.m. On a day. You have all of your X values, all of your individual samples, which are also going to be plotted directly onto the control chart without being averaged or anything like that. Again, you can sort of, if you compare this with your Xbar-R chart to this one, you have a whole lot less data. Therefore, it's also, you have less data being collected in between every radio produced. So you can probably already see that there's some issues here. You may want to increase the frequency if you're going to do this. And also, just by the very nature of an X and MR chart, you're going to have a lot less sensitivity to your process changing as it goes through when you're plotting your charts. Step 1, go ahead and calculate all of your MR values. Again, that's the point that you're taking that you've just plotted versus the previous point that you plotted right before it on the X chart. And again, your first value for any X and MR chart is always going to be null. There is no real actual MR value for the first sample in an X and MR chart. Step 2, calculate your grand average of your X values, your X bar, and also calculate your MR bar values, your moving range averages, and take care. Your X bar is going to be divided by 10 because you have 10 subgroups. Your MR bar, your average of your R values, is going to be divided by 9 because they will only have 9 values. Step 3 is you're going to go ahead and calculate your control limits, taking care to use proper values for your constants. Your E value, E2 in this case, is going to be equal to be 2.66. There is no valid value for D3 in this case, and D4 is going to be 3.267 when you have a subgroup size of 1 and a subrange size of 2. So go ahead and calculate your control limits, X bar plus E2 times your MR bar. That's your upper control limit. And X bar minus E2 times MR bar is going to be your lower control limit. And your upper control limit for your MR chart, your secondary chart, is going to be D4 times your MR bar value. And there's not going to be a valid value for your lower control limit. I'd really recommend, again, plotting your control limits first and taking care that the scaling is going to give you some room to actually plot your points on whatever grid you choose to use. If you use the SPC Fundamentals training guide, you should be given enough room in the example areas for you to be able to properly plot all of these points. after you plot the control limits for both your primary X chart and your secondary MR chart, then go ahead and plot your individual samples that you plotted, that you actually calculated in step 1. So here's the solution for the X and MR chart exercise. You have your X, or rather your MR values range between 1 and 20. Your X bar value is going to be 85.6-ish, depending on your rounding of the calculator you've chosen to use. Your MR bar value is 5.78. I bet you can probably already see that this is going to have a drastic effect, particularly that 20 right after that 1 between subgroup 8 and 9, but we'll see it on the control chart how it's actually going to affect things. Upper control limit should be around 101. Your lower control limit for your X chart should be 70.2. And your upper control limit for your MR chart is going to be 18.9. When you go ahead and plot your control limits and you go ahead and actually plot your X values and your MR values, you're going to go ahead and see that your process, when you start to analyze this, between subgroups 1 to 8 look pretty good. Something happened at subgroup number 9 where you were out of control for sure in your MR, in your moving range. The volatility of your process absolutely skyrocketed. And it shows up also in your X chart where you're actually starting to get low values and extremely low value. You would definitely want to investigate what happened over there to figure out why that was happening. And you really need to go in and actually look at what happened and not speculate like I'm going to be doing. I'm willing to bet that if I was looking at this data and I was just eyeballing it, your sizes, or rather your decibels for your radios were going fine. Maybe something went wrong in production, or maybe somebody knocked a setting wrong with one of the equipment used to manufacture your radios, and all of a sudden you had a huge sound amplitude. The volume was just way low for your radios, and then started maybe to pick back up again. You really need to investigate, which is what you would have been alarmed on had you run these charts. Up until now, we've been talking about X bar and R charts, X and MR charts. Those are variable control charts, and the vast majority of the time, those are the charts that you're going to be using in both your WinSPC implementations as well as just in general when you want to do any sort of metrics. Those are the easiest ones to do. Tend to be, again, the ones that are most common. However, there's a completely different set of control charts that you're going to use for a different type of data, for your attribute data, that you can also do, and you can do in real time with SPC as well and in WinSPC. Now, if you remember, attributes are quantitative data, or rather qualitative data. It is data that you can't necessarily put a measurement to or a number to, but you can definitely count them in some way, either true, false, yes, no, the existence of X number of these particular types of defects or defectives or things that you want are points of interest. There's two basic ways that you count attributes. You either count defects that are present on some mount that you're measuring, or you're going to count defective units. Now, there's fundamental differences between defects, counting for defects and counting for defective units, and therefore you have different control charts that present themselves, and it's actually extremely important that you always pick a valid attribute chart type when you are doing attribute charts. Otherwise, you may come to incorrect or misleading or blatantly incorrect conclusions if you pick the wrong chart type. When you have defects, you could have a single widget, and you're looking at this one widget, and I could see it has 3 scuffs, a scratch, 5 pits, and it's bent. So that would be a number of different defects on even a single unit. And you can expand that out. You could say I have 10 widgets, and on the 10 widgets I found 5 scuffs, 3 scratches, 100 pits, and some other defects that you're looking for. So your defect count can exceed the actual lot size, the amount of items that you're actually inspecting. Defectives is completely different. With defectives, you have a number of units that you are inspecting, and for each one of those units, it's either pass or fail. So you could have a lot size of 1. If that's the case, your only options are either it is good or it is bad. Either it is a pass or it is a fail. If your lot size is 100, if 3 of your widgets are defective, meaning they are just not good, or they have present on them something you're looking for, then you have 3 out of 100 are bad. You can never have more than 100 in that example that are actually bad. You can't count more than 100 for a defective unit count in that instance. Now, to simplify calculations, or conversely, to make your charts more meaningful if you're not able to do this, you actually have to pick different valid chart types if your lot size changes over time versus if your lot size is always constant. If your lot size is varying and you're using defective, and you're looking for defects, you need a U chart, or a U chart is one of the valid chart types. If you are counting for defectives and you have a varying lot size, you must use either a P chart, which is a valid chart type, or a Q chart. If, however, you are using constant values, you can actually start to make some assumptions with your calculations to make things easier, and therefore for defects with a constant lot size, you can use a C chart, and for defectives with a constant lot size, you can use an NP chart. P chart, P stands for percentage, NP stands for just a number, but a P style chart, meaning you can actually plot, rather than a percentage, you can plot an actual count out of some number like 47 or 50, meaning that you always have the same size. You don't have to use a calculated value. You don't have to normalize your data. Always pick the appropriate chart for whatever data you're collecting. You do not want to get into a situation where you are using an NP chart with a varying lot size. Your control limits will be meaningless. You don't want to use a U chart when you're counting defectives, and you certainly don't want to use a P chart when you're counting defects. I can give you a really great example that I once came across, and this was a real-world example where a hospital was doing wanted to do some SPC and do some comparative analysis on the different surgeons that were in that particular facility. And it was a fairly inexperienced person doing the initial analysis of these doctors, and what they ended up doing is they made their best doctors look horrible. They had one doctor who, for mortality rates, these were surgeons, they were checking the mortality rates. One surgeon had only 1 fatality during his tenure at the hospital, while this other doctor had 5 fatalities on his record and his tenure at the hospital. And he used a constant defectives chart. He used an NP chart. And it made the doctor who had 5 mortalities, which is horrible, you have 5 more people dead, than the other doctor who had 1 fatal surgery. However, what he didn't take into account was the fact that there was a difference in lot size. The doctor with the 1 mortality had only done 2 surgeries in his tenure at the hospital. His mortality rate was 50%. The doctor who had the 5 deaths on his watch had done over 100 surgeries with only a 5% mortality rate. It made their best doctor look horrible, and maybe the doctor with least experience look a lot better. So you have to be very, very careful picking your attribute control charts. And now we're going to go ahead and do an example of a P chart. Okay, in this example, we're going to go back to the pencils manufacturing again. Every day, the number of defective pencils is counted from an inspection lot size of 50. This might be at the end of a batch, or maybe you know that you make some set amount every time period. But ultimately, your lot size in this case is 50 each time you take this lot size. Your job is to plot a p-chart for the last 10 days worth of data. So here we have the data from January 1st of 2006 all the way until January 10th, 2006. Your defects range from your starting point 14 out of 50, then 8 out of 50, 7 out of 50, so on and so forth. And the last lot size is going to be 0 out of 50. And I think you're going to notice here that even just eyeballing it, you can probably see that the way this data was taken, that you started off and you had quite a few defects and seemed to be a lot of double-digit defects, and over time it seems to be getting better. By plotting this in the example, we're going to actually quantify this and see how our process is behaving. All right, now that we have our data, step one, we need to calculate the p-values. Again, what are the p-values? P stands for percentage. So we have, for the first number of defects, is going to be 14 out of 50, giving us about 28%. Next one's going to be 8 out of 50, so that gives us about 16%. We're going to keep doing this for each one of the lots. Step two, we need to calculate the average percentage defective. That's the p-bar value. So you take all of your p-values that you calculated in step one, add them together, divide them by your lot size, and you get a p-bar value. In this case, that's about 15%. That's your grand average, again, of all of your p or percentage values. Step three is to calculate the control limits for your p-chart. There's only a single chart in a p-chart, in an attribute chart. You don't have a component chart or a double chart like you do for variables. So you're just calculating your upper control limit, which in this case, the function for that is given here. Your upper control limit is your p-bar value, that's your grand average, plus 3 times the square root of everything underneath that radical, which is, again, the p-bar value times 1 minus the p-bar value divided by n, which is your lot size for each one of the quantity inspected. Really, really important to keep your order of operations here. If you are, it's going to be inside out, you want to go make sure you do your multiplication first, then go do the division after that by the n, then you do your square root, then you multiply that times 3, and then you go ahead and add that to your p-bar value. In this case, go ahead and calculate your upper control limit to be 0.3 or 30%. You do the same thing with the lower control limit. The only difference is instead of adding that function, adding that 3 times the square root of the p-bar minus 1 minus p-bar over n, you're going to subtract that value. So if you record what's underneath that radical, it'll actually save you a little bit of time. It's, for short, your control limits are p-bar plus or minus that value that's going to be your control limits. Step 4 is going to actually plot the chart. Personally, I like to draw the control limits first, make sure I get my scaling down, then I'm going to go ahead and enter in the individual values for my individual lot numbers for each one of the percentage for each lot number. Once you do this, you can then begin to analyze what you see on the control chart. And again, we're seeing sort of what we saw by just eyeballing the data when we were looking at it. You started off, you were in what was considered statistical control from your historical information, meaning you were behaving what we would call normally. But as we progressed through our process, we were getting better and better and better until ultimately the most recent subgroup, we actually had no defectives at all. Quick note, something to recognize, you cannot, in a percentage chart, get negative values. That doesn't make sense. Even if your lower control limit did equal 0, that is technically within control, and that's an important distinction to make when you have control limits, that if your value happens to equal the value of your control limit, that is still considered an in-control point, particularly with well, in all cases, but particularly it becomes makes sense with percentage charts. That's not to say you can't have a process where it would actually be unusual to have no defects. That can occur. Hopefully it doesn't. Hopefully you do have a process that is capable enough that you're not producing, that it's not expected that you produce defects, but there are processes where that is in fact the case, and actually finding less than normal defects would be cause for alarm, maybe to figure out if maybe there was just some abnormal circumstances or maybe an incorrect reading or maybe even somebody was fudging the data. So very important to look at even situations where things are behaving maybe better than you would expect. Because your ultimate goal is to find out, is your process stable and is your process beginning to shift or change? Is there any non-random variation that is acting upon your process? And in this slide, you can see that how WinSPC would display this data if you were to have entered this data directly into the software. The advantage of going and calculating and putting this data into the software, you didn't have to calculate any of the limits yourself. All that was done programmatically. The software did that for you. And for each data point, you actually would have had the opportunity to see in real time if you had violated those historical control limits. So not only would it have been easier for you to do and less time consuming, but it also would have given you feedback sooner should you have violated historical control limits, hence the real-time aspect of SPC as opposed to the after-the-fact analysis aspect of SPC you would do if you didn't have a software package like WinSPC. So here's an exercise for a P-chart. It is very, very similar to what you saw in the previous example. So I encourage you to go look back on that on the methods and the procedures. It should be pretty much the same. Numbers have been tweaked, and the conclusion you'll find is going to be a little bit different than it was for the exercise, for the example rather. In this case, we're going back for this exercise to the defective radios example. This time, the number of defective radios is counted from an inspection lot size of 20. Plot a P-chart for the last 10 lots. And here are your lots ranging from lot number 121 all the way down to lot 130, and you can see all the number of defectives out of your quantity inspected each time. It is very important if you want to use a P-chart that your lot number be exactly the same. There can't be any deviation in your lot size. If there is deviation in your lot size, you can no longer use a P-chart. You need to use one of the other chart types listed earlier on, and you're going to need to keep very close track of how many were actually inspected at every time. You would have used an NP, a normalized P-chart, or a number P-chart, which is going to give you, instead of a relative percentage, giving you a complete percentage, but that's beyond the scope of this particular exercise. Remember, this is a 4-step process. Step 1, calculate your p-values for each lot. Step 2, calculate the p-bar value for the lot as a whole. Step 3, calculate your control limits, both your upper control limit and your lower control limit. Finally, step 4, go ahead and actually plot your chart. Again, you are free to plot your data points first or plot your control lines first, but from a best practices standpoint, you will get more value out of this if you plot your control limits first, then plot your data. Finally, you're going to want to go ahead and actually analyze the data after you've gone and plotted. And here is the solution for the exercise. So we've gone ahead and plot the solution or the graphing of the control chart. Now we can't absolutely know what was going on here, but we can make some inferences from what we see. It is your job as a quality expert, a quality engineer, to go in and actually begin to investigate what you see here. The control limits are going to be, for the lower control limit was less than 0, meaning we would expect that getting no defects is within historical norms or is normally distributed data. Your upper control limit is at around 40%. Subgroup 1, 2, and 3, they weren't so great, but you had some defects present. Subgroup 4 and 5, you actually didn't produce any defective units at all. But it looks like something went horribly wrong and you started making bad radios again, and maybe somebody adjusted it at around subgroup number 8. Can't know for sure. Everything is within historical norms, so there's not really you don't necessarily, from what this data, there's nothing that would indicate that you would need to adjust your process. Even though you started seeing at subgroup number 8 that you're starting to get, really close to your control limit, it is still it is actually within the control limits. You would not recommend that you try to tamper or intervene necessarily based on this information. It isn't to say that you probably don't want to figure out why the quality changed over time, but as far as an alarm to immediately act and immediately change something, that we can't gather from just this information that we have here. Okay, so a little bit of a wrap up about control charts. What are some of the advantages and disadvantages? Well, advantages using a control chart. First off, you're going to use this to monitor and control ongoing processes. It gives you a way to act on situations where your data is behaving, where there is non-random variation within your process, and it also, in turn, gives you the freedom to ignore data that is falling within natural norms, that is just random variation. To chase or to try to correct for random variation that is inherent to the process is to effectively chase your tail, and the control charts, if implemented properly, can allow you to not have to overcorrect and not tamper and make your process worse than it would have been had you just left it alone. Disadvantages to the control charts are, again, just because the controls are what they are doesn't mean that you may not have external checks. However, if you start controlling too often or you put on too many of your control rules that you're looking for, you're going to start getting false positives, and you start responding to false positives, you will become the source of variation. It is very important to have a rational subgrouping. It is very important that you make sure that you are collecting data at a sufficient rate where you can actually respond to out-of-control indicators, but not at such a high rate, not at such a low rate that too much product has been processed without having been actually tested for the control of the process. You need to have that happy medium where you're getting a good representative sample. You're going to want to make sure that you can choose the right control chart for the correct type of data. If you're doing this by hand, this is very important. If you're using software such as WinSPC, this will not be an issue, as WinSPC will not allow you to choose an incorrect chart type that could lead you to incorrect conclusions and invalid conclusions. You want to make sure you decide that subgroup size as well as the subgroup size before setting up your data collection. If you have to change it after the fact, it's the equivalent of comparing apples to oranges. You're effectively measuring a different process. The math completely changes. You're going to need to start a new collection, in WinSPC terms, you're going to have to collect for a new variable. You do not want to compare control charts from subgroup size of 1 to a subgroup size of 2 to a subgroup size of 3. They're not comparable.